All right, so we're going to have some physics notes. This will be journal number 23. You should have out in front of you the notes that go along with this that say velocity, speed, and acceleration up at the top. And let's get started here. So you'll see up at the top of your notes in gray, I believe, in a gray box there, the first main principle here. Physics is the study of moving objects. So here in physics, we want to be able to predict how objects will move in all different situations. If at any point you want to pause or rewind, feel free to. I'll also post just the notes here, the PowerPoint on It's Learning. If you want to just go back through at your own pace, you're welcome to do so. And I encourage you to, especially maybe to help you review or study. All right, moving right along here. Question for you. How do you know if an object is actually moving? Be prepared to have your brain blown just a little bit here. How can you know? Think about it. You're probably thinking, okay, if I get out of my chair and I move, I've changed position, so yeah, that would mean I was moving. But when it's changing position, traveling a certain distance, we often call that moving. But what if a person's just standing still? Are they moving or are they not moving? Let's look at this a little bit further. What about if I'm standing perfectly still, but I'm on the planet and the planet itself is moving? So therefore, are you moving? Gets kind of tricky here, because then the planet itself is moving around the star, the sun. So then is the sun really moving or is it stationary? You can see how this might start to get a little confusing. So does that mean everything is moving? If the sun is moving, it's part of a solar system that is part of the Milky Way galaxy and it is itself moving within the universe, so then is everything moving? Welcome to physics and the confusion that might ensue. So here's what we can do to know if something is really moving. In physics, to kind of clear this up, we use a principle called point of reference. Now hold off on writing down any definitions yet. On the next slide will be your first definition for point of reference or reference point. But in general, a point of reference is essentially just what appears to be moving to you. So here we have some rowers. It can be really tricky to tell what's moving and what isn't. Are the passengers in a boat moving compared to a person standing on the shore? Or is the person standing on the shore moving compared to the rowers on the boat? So if you think about it, if I'm standing on the shore watching some rowers go by, it looks like the rowers are moving. However, if I'm in the boat rowing and I look at the person on the shoreline, it looks like the person on the shoreline is moving. So it's all about your point of reference. Now, the hands on a clock don't seem to move, well, especially the hour hand. However, we know that they are constantly moving very, very slowly. So let's get a definition here. A reference point. This is under words you need to know, number 1, reference point. It is a place or object used for comparison to determine if something is in motion. So another way to think about this is an object is in motion when it changes position relative to a reference point. So if we look down here at the picture, your tree would be the reference point here. And here's our little caveman running away. If the reference point is the tree, it wouldn't be moving. Therefore, we know that the caveman is in motion. So again, a reference point is a place or object used for comparison to determine if something is in motion. So it's all about having a reference point and using that as a kind of comparison for other objects. Again, if you need to pause at any point, feel free to. Moving on, back up to the top, looking at those last couple main principles, number 2 and 3. Basically, if you really think about it, all objects are moving some amount all the time. So, as we were talking about earlier with, it looks like we're standing still, but yet we're on the earth, so the earth is moving, so therefore we are moving, and the Earth is moving around the sun, and the sun is part of a larger system that is moving in the galaxy, which is in the universe. So, if you really think about it, everything is moving all the time. The only way we can really compare and know motion, number 3 here, we compare the motion of the object that appears to move to a stationary object. Now, down below that next term, stationary object, number 2, and the words you need to know, here is its definition. It is an object that doesn't appear to move. That's all stationary means. So it appears not to be moving. We might know that in reality it is, it's some, to some extent, but it isn't actually moving. Now, if you want to think about it in another more weird way, if you look at your table, it looks like it's not moving, right? It's a hard, solid object, not moving, hopefully, unless you're shaking it right now. But what is everything made up of? Everything's made up of matter, right? And what makes up matter? Atoms. Atoms are what make up matter. And then if you think about what makes up atoms, you should be thinking electrons, protons, and neutrons. Yes, that's what makes up atoms. And are electrons not in constant motion? So therefore, really, even your table is moving. Even though we can't tell it, it looks solid, looks like it's not. It, in fact, itself is in constant motion too. Just another crazy idea for you. All right, now, an object is moving slowly if it moves a short distance in a long period of time. So think about someone, tiptoeing across the classroom. They would be going slowly over a long period of time. Or an object is moving quickly if it goes a long distance in a short time. So when you, throw a football down the field, it is moving a long distance in a very short period of time, so we would say it's moving quickly. Now, there are several ways we describe the motion of an object. Here are 2 of the important points here. Velocity and speed. Your definition, number 3 here for speed. Speed's definition is it is the distance traveled in a certain amount of time. Distance traveled in a certain amount of time. Compare that to velocity. Velocity's definition, number 4, it is the speed in a certain direction. So, be thinking, what's the difference really between speed and velocity? The only real difference is the fact that velocity involves direction as well as speed. So, velocity is, how far you traveled in a certain amount of time in a certain direction. Now, a lot of times these are going to be very similar, and they are sometimes even used interchangeably depending on, what the purpose is. But sometimes it can be good to tell the difference. So if you think about, a car going down the freeway at 60 miles per hour, that's its speed. And if it's, going north at 60 miles per hour, that's its velocity. I added a direction there. Now, let's say the car is really, starts to turn and it goes, northwest at 60 miles an hour. Well, its speed might still be 60 miles per hour, but it is no longer headed north at 60 miles per hour if it's going northwest. So its, velocity towards north would be different. It's easier to explain on the whiteboard, obviously. Sorry, I'm not there to do that. So, moving right along here, the formula for speed. Speed is distance over time. Now you see the M and the S there. That's just an example of what your units might be. It might be meters per second. So think, what are 2 ways that you could increase speed?
Please pardon this interruption.
Pardon the interruption here.
Our dinner is here. If you are presenting tonight, please come to the office.
Sorry about that. So 2 ways to increase speed, making something go faster. Looking up at your formula up above, think what you could change as far as distance or time that would make your speed go faster. One way is you could increase the distance traveled in the same amount of time. So if originally I was going 2 meters in 1 second and now I'm going 6 meters in 1 second, that would mean my speed had increased. Can you think of the second way? Second way is to decrease the time it took to go the original distance. So if I originally took 2 seconds to walk 6 meters, but then I speed up and suddenly I'm able to go 6 meters in 1 second, that would be an increase in speed. All right, so moving on here to graphing velocity. Now this first graph you are not going to draw into your notes. This motion on day one does not go in your notes, but just watch along here. So graphs are really useful to help us know what actually happens. A lot of times it's a lot easier to see, kind of determine velocity and speed and things like that looking at a graph rather than just a data table. So the shape of the line and steepness of the slope can tell us what has happened and how fast it occurred. So we are not done with graphs, unfortunately, in science here. We are just getting into the thick of things. So what you want to be able to do is know what the graph is telling you just by looking at the line. Let's look at this. So go ahead and draw this into your notes. You're going to have 3 lines, 3 straight lines going up at different slopes. One's steep, one's kind of in the middle, and one's a little bit of a lower slope. So the important thing here, you have your 3 lines, but also make sure you have your labels. Distance on your y-axis compared to time on your x. Very important knowing what you're looking at. You need to be able to interpret distance and time graphs here. So let's look at this. You can use the slope of the line to find its velocity. Again, distance over time. So if I look at this steep line here, I can go 15 meters in 5 seconds. And if I simplify that, really I'm going essentially 3 meters per second. That would be my velocity, 3 meters per second. So velocity is going to oftentimes be in meters per second, centimeters per second, in your graph and things like that. Let's look along here. More distance in less time. That means it is faster. I would add this into your notes right here. More distance in less time means you're going faster. If I go over less distance, so I'm only going 5 meters and it takes me 15 seconds, that means I'm going slower. Less distance in more time is going slower. All right, now think of the velocity on the graph in this way. Which, if I put some balls on each line here, which ball would go the fastest? If we let them go at the same time, it's pretty obvious, right? The one up here at the top is going to go much faster than the one down here did. So that can kind of help you as far as thinking about velocity and speed. If you imagine putting a ball on the line and saying, what would it do? So the graph with more steepness is the faster velocity, the less steep, the slower. Now this is the next graph. This is going to go directly under that first graph that you drew. This is, again, interpreting speed on a graph. Same axes labels, distance versus time, but here you're going to draw a gentle slope followed by an area of a horizontal line, so no slope here, just a straight flat line, and then a steeper line up at the top. All right? Now, as a group, or on your own here, describe how fast the object is probably moving as you travel along the line, going from left to right. Think about what is occurring. How is the object moving? Is it speeding up? Is it slowing down? What's happening? Let's take a look-see here. All right, so it started out slowly, right? It's going, 5 meters and takes about 10 seconds, so that's pretty slow. But then, in the middle, it completely stopped moving. You might have thought, oh, it slowed down, but it's not moving at all. Here's why. It's still at 5 meters, but time is continuing by. If your distance isn't changing, but time continues on, guess what? You are at a standstill. And then picks back up at the end, goes much, much faster. So, again, if you think about putting a rolling ball on the slope and thinking about what would happen, this ball would start to roll slowly down. The ball in the middle wouldn't roll at all. And then the ball up at the top would roll fast. So you can, again, that might help you think about what would happen as far as velocity goes. So what should you learn from this? Steep lines on motion graphs mean that the object is moving quickly. Non-steep lines mean it's moving slowly. And straight, flat, no change in slope lines mean it is not moving at all. So now let's think about if we wanted to graph speed here. Add some distances on here. And if I wanted to graph this data, it would kind of make almost a straight line. Not perfect, but pretty close to a straight line. So this is your standard distance versus time graph here. Distance versus time. Now, this is basically the line you see in the data table. It can change really quickly if I pick different variables to graph. So if I swap out, instead of graphing distance, now I'm graphing time against speed, notice what will happen. If I look, it's the same information, but now I'm just looking at speed rather than distance. And suddenly I should have an almost straight line. It's not a perfectly straight line. There might be a couple little ripples, but generally speaking, straight in comparison to the time versus distance graph. So the two lines look different, but still describe the same object's motion. So essentially it had maintained a constant speed here. That's what that straight line means in this case. All right, so goal here, you need to watch your variables carefully. Look at what your graph is. Is it graphing distance and time, speed and time, velocity and time? Look at what it is graphing. Now, on to the last bit here, acceleration. All right, so if you think about balloons, think about how they move. What do you think? When you have a standard balloon filled with helium, you let it go, it's going to go all over the place. Depending on wind, it might go this way or that. Generally speaking, it goes up, but they kind of just can move all over. So, question for you. Do you think they move at a constant speed or direction? Remember, constant means staying the same. So they just kind of move all over the place. Sometimes they go straight up, sometimes they go crazy. All right, now defining acceleration. A lot of you probably just say, oh yeah, accelerate, it means you speed up, right? If you accelerate in a car, you're pressing the gas, you go faster. I'm here to tell you that definition is not complete. You need to change in your mind what acceleration is. It can mean speed up, but it also can mean a bit more. So your definition here for acceleration is the rate at which velocity changes. This is number 5 in your notes. The rate at which an object's velocity changes. And you might want to add in a little bit more here after you watch this. So we'll turn up the sound here because sound effects are fabulous. So it can mean speeding up. But it can also mean slowing down. And finally, changing direction. All 3 of those are in fact velocity changes or acceleration. So I would add this to my notes. The rate at which velocity changes. It can be speeding up, it can be slowing down, or it can be changing direction. All 3 of those are acceleration. So when a bus slows to a stop at a bus stop, that is a change in acceleration. That is still acceleration. Velocity has changed, so it has accelerated. We might call it deceleration. So, good things to know here. Acceleration is just a change in velocity. You already have this equation. Velocity is distance divided by time. Your formula for acceleration is delta velocity over delta t. That little triangle, we call it delta in math and physics, science. You probably know what it means if you've been calculating slope in math. It does indeed mean change. So, acceleration is just the change in velocity over the change in time. Now here's something a little bit important. It's going to look like this, and this you also want to add to your notes. It is the final velocity minus the start. And the final time minus the start time. The order does matter, just like when you calculate slope. Sometimes you get negative, sometimes you get positive, and it does matter. So here you need to remember, final velocity minus the start velocity. All right? Get that down in your notes. Ooh, one thing I wanted to add here. You notice my units are meters over seconds squared. If you can think about why would it be seconds squared rather than just plain old seconds? Maybe you know, maybe you don't know. But in general, you should recognize acceleration being over, a unit over a unit squared. All right, now interpreting acceleration on a graph. Don't graph that straight line just yet. If I have a nice straight line, that's showing that the object has a constant velocity. If it's a distance in time graph, that means it's traveling at a constant velocity. If it's going constantly at the same velocity, is there an acceleration there? No, there isn't, because it's constant. There's no change in velocity. And remember, acceleration is a change in a velocity of an object. So if you want to have a acceleration shown on a graph, you will see a curved line. And this curved line you're going to draw as your first graph. This line here is curved, and it is showing a positive acceleration, meaning an object speeding up. It goes from, let's estimate that like 1 meter in 5 seconds. By the end, it's going much, much faster than that. So I would draw a curve, and I'd write down curved lines mean a change has occurred, which means acceleration. Velocity changing is acceleration. Now you could also have a deceleration or a downward curve. It's possible for an object to have a negative acceleration, meaning it slows down. This is what you saw in your lab last class with the cars. They slowed down. So you might expect to see a graph where it is decelerating. All right. So last bit here, do you really notice when something speeds up or slows down? This is a video thinking about perceiving acceleration in class. We kind of tried this out yesterday, but I'm not there to try it out with you. If you want to try it out after watching the video, find a partner, have them, do this and watch their eyes and see what's going on. But it's just kind of something interesting to think about. I will post this perceiving acceleration link on It's Learning if you would like to watch. It's about 3 minutes long. It's kind of interesting. I'd recommend it. So that takes care of today's notes. Again, if you are wanting to go back, rewatch anything, please do. I will also post a copy of the kind of key to the notes probably tomorrow. So if you want to check yours against mine, you can do that then. All right, that takes care of it. Hope you enjoyed. I'll see you all on Monday.